Today we're going to talk about the piecewise function. So it is a special function, and the definition of the piecewise function is a function that combines a few other functions. So it is a function formed by different functions. So for example, this is a piecewise defined function, and one characteristic of the piecewise defined function is that it contains this symbol over here. So it is y equals, but it's not only one function, but it can be 2, 3, or more than 3 functions. And each function works for the domain that it's explicit on the right side of that function. So for example, x squared, we know that x squared is the pattern function of a quadratic. So it's this parabola. And this is the parabola that works for every value to the left of x0. So x0 can be any value. In this case, well, x0 is usually one number, but let's say x0 is, I don't know, 1. So x squared is a function that works for every value on the left of 1. And then negative x squared plus 3x, that is a parabola that up and downwards, is the function that works for the values that are greater or equals to 1, or x0 in this case. So that's why here we have a point over here, because at x0, at exactly x0, the second function is the one that works, okay? The domain in this case is all the real numbers, because you can have values from negative infinite to positive infinite. And the range also, if you scan the y-axis, the range also can have values from negative to positive infinite. Where do we use these functions, or how can we know, or how can we let's say, use this function in a real life situation? And this is an example of a real life situation. It says Bob starts out for school at 7 a.m. and drives 10 miles in 15 minutes. He then stopped for 30 minutes at a local restaurant, and then he continued driving a little faster, another 20 minutes, and covered 18 miles. At which that point her car breaks down. So from that point he jogged, he ran to the school, and he did 45 minutes to the last 3 miles. So the exercise asks us to draw a graph with the distance on the vertical axis and the time on the horizontal axis. So let's say x is the horizontal axis and y is the vertical axis. So x is the time. He drives 15 minutes, and in those 15 minutes he completes 10 miles. Then he stopped for 30 minutes or 30 more minutes. So 30 minutes after that he didn't move because he was taking a breakfast. Then another 20 minutes, and well, these are 30 minutes more than 15. These are 20 more minutes. He did 18 miles after the breakfast, and then he spent 45 minutes or 40 more 5 minutes and to complete 3 miles. Okay, so I'm going to try to do my best in order to draw. I'm sorry for my drawing, but this is x, this is y, and we're going to x is the time, so I'm going to do "15 minutes "15 minutes, 30 minutes, 45, 60, 75, 90, 105. And in the miles, we're going to write here 10 miles, 20 miles, 40 miles, and that's it. So the first 15 minutes he drove 10 miles, then he spent 30 more minutes. Let me erase this. Then he spends 30 minutes, so from 15 to 45 without moving. Then he spent 20 more minutes, so from 45 to 65, and he did 18 kilometers, 18 miles, so 10, almost 40 here. Almost 40. Then he spent 45 minutes, so since 65, 20, 30, como por aquí, y solamente recorrió 3 millas, más o menos, okay? So this is an example of piecewise defined function. Each part of the function, even if we don't have the function itself, you can see that this is a line that it has a greater slope than this, which slope is 0 because it's a constant function. Then the slope is greater than in the first part, and then the slope is almost 0, but it's a very few slope. So this is an example of how a piecewise defined function can be. And let's talk about domain and range. Domain and range, well, you have to pay attention on which parts of the domain are the x values on the function. So for example, for this piecewise defined function, the domain starts at -4. So x is an element from -4 with a parenthesis, because we have a hole over here, and that hole means that you are not touching it, to -2, and -2 also use a parenthesis. And then union, we also have values for x since 1 with also with a parenthesis, 2, 3, and with a close interval because we have a point, a solid point over here. And with respect of the range, the values for y that this function can have is from -5 without touching it, so will be -5 to, and the maximum point that the y touches is the 4. So it is till 4 with closed, or yes, it's a closed interval or bracket because this is a solid point. The range of this part of the graph, it's already included in the other part of the graph. So that will be the range in the domain. We can have, for example, let's do the graph. I'm going to do my best. This is not easy for me to sketch the graph of this, but let's see this. The function x squared plus 1, it's a function that starts over here. So it is a function like this, okay? And this parabola that opens upwards and has its vertex at 0, 1 will only be useful for the interval for the x that are less than 1. So let's say this is 1, this is 1, let's say this is number 1. So the rest of the function, I will use this function over here, this part of the function, and the rest of the function, the values that are more than 1, I'm going to erase it, okay? I'm going to erase it with this. So the graph only, that graph only is used, but the values, or with the values that are less than less than 1. Then I'm going to use 2, and it says 2 if x is equals to 1. So when x is equals to 1, the value will be 2. Let's say the value 2 is here. So we will have a point over here at 1, comma 2. And then x minus 5x if x is more than 1. So this function over here crosses the y-axis at 7. So this will be, and then 1, 2, 3, 4, 5, 2. So let's say it is a line like this, okay? But that line will be only for values that are more than 1, okay? So my values from 1 to the right of 1. And the values that are less than 1, I have to erase them because those are values for the other two functions. Oh my gosh. Okay. Se borró todo, pero más o menos esa es la idea, okay? So this function will be a parabola until 1, then a point in 1, and then a negative line in with the values after than 1. This is an easiest one because it has 3 constant functions. I'm going to try. Okay, so this function will be this is my x-axis, this is my y-axis. Oh, I'm doing another one. This is the function that I wanted to do. So my constant function y is equals to -2 for values that are less than 1. So if here we have 1, you have -1, -2. The constant is an open interval, and then to the left of that open interval at 1. Then f of x is equals to 3, 1, 2, 3, if x is exactly 1, so we have a point over here. And then we have that f of x is -3 for the values that are greater than 1. So from 1 to the right, that is the function, -3. Okay, another possibility of Alex exercise is that they are asking you to substitute values. In that case, you don't have to do the sketch of the graph, you just have to substitute. If we are looking for h of -2, we have to look h of -2, we have to pay attention in which of the 3 roles it's -2. And this is the rule that I'm going to use because it says if x is greater or equals to -2. So I'm going to use this over here, this rule of correspondence, and I'm going to substitute -2. So this is going to be -2 minus 1 squared minus. So this is going to be -3 squared, and that is going to be -3 squared is 9. So h of -2 is going to be -9. H of -1 is going to be in this interval, okay? So in order to solve h for -1, I'm going to substitute it on the first rule of correspondence, and that will be -1/2 times -1 plus 2, and that will be -1/2 plus 2, and -1/2 plus 2 will be -1/2 plus 4/2, so it will be 3/2. And finally, h of 2, and h of 2 I'm going to substitute in this function, h of 2. So h of 2 will be equals to 2, and there's no other thing to do because you already have the 2. It's a constant function. For all the values of x that are more than 1, the result or the y value is just 2. Finally, you have to determine in the intervals in which the function is increasing. Increasing means that it is having a greater value than in the last point. So as you can see, in this specific interval, the function is increasing, and from 3 to 5, the function is increasing. So the interval of the function increasing will be from -4 to -3, union from 3 to 5. And that's the interval in which the function increases its values. Remember that the intervals are always given by the x values, and you have to pay attention on the y values in order to see if they are increasing its value or decreasing its value. So this function is decreasing because it is getting lower values of y, then increasing, then decreasing, then constant because the values of y are not moving, and finally increasing again. And that's it. Those are all the types of exercises that you can have in a NALEX exercise. Thank you.